Assalamualaikum warahmatullahi wabarakatuh. A very happy day. We are going to continue in for membrane technology, but focusing on gas separation. As you can recall, before this, there is 2 lectures before this that emphasize the membrane technology application only in water purification, basically. So this point forward, we are going to learn about the membrane technology application that specifically on gas. Okay. So alright. So basically in this topic in gas separation, what you should note at the end of this topic is you should able to identify the membrane materials and also membrane process design. Secondly, you should able to differentiate the polyamide membrane, carbon membrane, and also polymeric membrane. And thirdly, you should able to evaluate the potential use for industrial application, specifically in gas separation. Alright, before that, first of all, you need, I'm going to introduce the gas separation first. So basically the gas separation, what you mean as gas separation, you mean there is a mixture of gases. I can give example, the gas is CO2, carbon dioxide and a nitrogen, a mixture of that, and you want to separate it with two. So what are the driving force of this membrane for gas separation? So basically driving force is transmembrane pressure. What is that mean with transmembrane pressure is let's say this one is your membrane, right? Okay, this membrane comes in, sorry, the gas go in and this one is gas go out. This one is your permeate. Alright. So P permeate here and P in here, the difference between these two pressure is called as transmembrane pressure. Okay, the difference between these two are the driving force of the gas separation can be occurred. So what is separation's principle? So basically there are two types of membrane that they are being used in the gas separation. Firstly is non-porous membrane, which is the membrane top layer that is 100% thin layer, which is there is non-porous, there is non-pore existing on top of the layer. And secondly, there is also porous membrane, which is there is a pore on the membrane, the surface of the membrane, where there can be 3 types of separation can occur, which is one is convective flow, secondly is diffusion, and lastly it may also occur based on molecular sieving principle. And how we are going to differentiate between these 3 is based on the pore size of the membrane being used. Okay. All right. Basically in gas separation, there are 3 types of membrane can be used, which are one is we call as metal membrane, second is polymeric membrane, thirdly ceramic and zeolite membrane, and finally we call it as a mixed matrix membrane. Okay. Selective layer. What does that mean with the selective layer? That means a layer that can absorb or can attract the attractive gases that you targeted to separate. So basically, there are few. Sorry, this one is not selective layer. It is selective layer. My apologize for this. Okay, there are few types of the layer that been used widely in the industry, which is we call it as PDMS, PPO, PTMSP. This one basically is rubbery. okay, rubbery. And secondly, we can also use glassy polymer, which is the example is about polysulfone, something like that. And for the selective layer, basically the top layer, the thin top layer on top of your membrane, actually the thickness is between about 0.05 to 0.1 micrometer. It's very thin layer, because if you have really thick layer, it's going to have a resistance towards your gas membrane. Okay, so we are going to learn about the permeation theory. What is permeation theory actually? Is what we call as separation principle. Okay, this is related to separation principle. Okay, the separation principle can I just mentioned just now, it can be occurred in two types of the membrane. One is non-porous, or we call it as dense. Another one we call it as a porous membrane. Okay, this one is second one. As you can see here, for the first type, there is non-pore existing on this membrane. But while in here in porous membrane, as you can see here, there is a circle, black circle here, this dot here, that is a pores. Okay, that's why we call it as porous membrane. But for non-porous, there is zero pore on the membrane. So that we call it as non-porous membrane or dense membrane. Okay, okay, we go one by one first. So basically, this is the difference between gas transport in different type of the membrane pores. Okay, this one, where's my second? Okay. Okay, this one, the first one, if you can see, this is your pore. Okay, this is your pore, and this is your also the pore. But these two membrane, the difference are the pore on the first membrane is bigger than the pore on the second membrane. Okay. Meanwhile, in here there is non-pore. There is non-pore existing, which is a dense membrane. So that's why the arrow here is meaning the reducing in pore size is bigger than the second one, and the second one is bigger than the dense, of course, because there's non-pore here. Okay. Alright. So when you have so because of the different pore size of each membrane, they are going to follow different type of gas transport mechanism. Okay, the bigger one we follow Knudsen diffusion. The medium, the intermediate pore size we follow molecular sieving, and non-pore membrane will follow solution diffusion mechanism. Alright, so let's test yourself first. What is the flow type of this membrane configuration, where you have the permeate flow is tangentially flow through uh, your membrane surface. So test yourself, what is the type of this membrane configuration. Either is can be dead end or cross flow configuration. So if your answer is dead end membrane, so that's your answer is wrong. Okay, you need to recall back. Okay, next. Okay. Okay, in Knudsen diffusion, the pore size is actually larger than the gas molecule, where the gas molecule is larger in kinetic diameter. Okay, in molecular sieving, the pore size of the membrane actually larger than slightly larger than the molecule size here. Remember, the Knudsen is bigger, molecular sieving is slightly bigger, but in dense or solution diffusion, the pore size is too small, or we call it as non-porous because we cannot see by naked eye or also using the SEM testing. Okay. So first we are going to go to understand more about Knudsen diffusion, where we have your pore size is bigger, substantially bigger than your molecular gases size. Okay, the pore size actually of the membrane is between 10 to 200 angstrom, or means below than 0.1 micrometer. Okay, the separation achieved when the gas collide, this is your gas, collide with your membrane pore wall. Okay, this one is your pore and your wall here. The collision, because when your gas molecule is moved move in different direction, is going to collide towards to your pore membrane wall. So this is how the separation can be occur. The transport rate of any gas is inversely proportional to the square root of its molecular weight. This is based on Graham's law of diffusion. Okay, this is the mechanism. At every collision of gas molecule and the membrane wall, actually the gas molecule momentarily absorb, okay, in this absorption here, and reflect, okay, at a random direction. Okay. However, collision between the gases, these two gases are rare. Okay, because these gases are moved independently. Okay, since the gas mixture, the gas molecule, these two gas molecules have different size, because it's different species, right? Of course, they have a different species. Then the average velocity of each molecule is different. So that's why the separation can be occur. Okay. However, by using this Knudsen diffusion, the separation is quite impossible, right? Because your molecules is freely move to any direction. Okay, it can be there is some separation will occur between molecule gas A and B, but it's quite very low because the molecules still can go further into your pores of the membrane. All right. So the second mechanism, the second type of mechanism is, we call it as molecular sieving. Okay. Remember, molecular sieving, the pore size is slightly bigger than your molecular size of the molecule. And the pore size of the membrane in molecular sieving is actually smaller compared to the membrane that we use Knudsen diffusion separation method just now. Okay, so the pore size of this kind of the separation mechanism is around 5 to 10 angstrom, and the separation achieved based on the difference of the molecular size. It because it's more, the pore size is smaller, right? Compared to the one that we discussed just now, is Knudsen diffusion. And this type of separation is 100% reduction is impossible but not unlikely. And basically, we are using this type of the mechanism by using inorganic membrane such as ceramic membrane. Okay. Okay, next we are going to learn the third mechanism of separation is solution diffusion. Okay. Okay, remember, solution diffusion is gas separation that occur through a non-porous or dense membrane, which depends on the difference in solubility and permeability of the gases for the given membrane. Okay. for each of the, if we're talking about the polymer membrane, each of the polymer membrane have different solubility and permeability for different gases. Okay, let's say I'm talking about CO2. CO2 towards permeability on the PVDF membrane. The solubility of CO2 is different on the on other type of the polymer membrane such as polysulfone or etc. Okay, that's why the gas separation using this mechanism is quite successfully and been used widely in industry. Okay, so how the mechanism of this type of solution diffusion. Okay, the permeates, which is the gas molecule here, okay, is a gas molecule, dissolve. Okay, it dissolve in the membrane material. So this one is your membrane, right? Okay, the first thing occur is this gas is dissolved in the membrane material. Okay, and then it diffuse. This one is diffusion, take over through the membrane material. After it reach it at this point, what will be occur? Then it's going to dissolve back. Alright, dissolve back to the permeate side. Okay, this one, if you can see that one, my okay, this one where you have a pore on your membrane, and this one is none, or is no pores at all. Okay, this one can, the expression can be occur when you collide the gas collide with the membrane wall. But this one, you need to, the gas need to diffuse, the gas need to absorb towards the membrane material and dissolve back to the permeate side. Alright, so since I explained to you just now, the gas is going to diffuse on the through the membrane material. So diffusion is actually the basic of the solution diffusion model. Okay, that's why we call it as solution diffusion. Okay, uh, the molecule is transported from one side to another side. It's based on the concentration gradient, which is concentration of the gas in this side and that side. Okay, so this one I think you have learned before. You should learn with uh, Dr. Kartini about the gas separation, focusing on solution diffusion. No gas separation lah, basically. So I just summarize back. The flux of species gas I through the dense membrane is following this equation. Okay, the standard equation. Okay, what is Ji? Ji is the flux. Okay, molar flow rate or molar flux of the component in standard temperature pressure of the species I. Pi naught and Pil is the partial pressure of the gas species I on either sides of the membrane. Okay, so imagine this one is your membrane and this one your inlet side, this one your permeate side, or we call it as out. So this one is your Pil, this one is your Pio. Okay, or either or lah. Okay, so L is the membrane thickness. So the thickness of the membrane here is called as L. Okay, D is what we call as permeate diffusion coefficient of species gas I, and K is the absorption coefficient of the species I. Alright, so just remember that those value of Ji, Di or Ki, it should be in standard temperature and pressure. So what is STP actually? So STP is the standard as a standard temperature and pressure, which is the standard temperature, it should be at 0 degrees Celsius, and standard pressure is at 1 atm. Okay, so the multiple of uh, diffusion coefficient and also sorption coefficient is we call as permeability. Okay, P. So the permeability is that measure the ability of the membrane to permeate the gas. Okay. Uh, okay. Next, we are going to learn about membrane selectivity. Membrane selectivity is an ability of a membrane to separate two gases. Okay, I and J. Let's say we're talking about gas I and gas J. Then selectivity means which gases that the membrane can allow to permeate more. Okay, I or J. So let's say that this one called as selectivity I to J. This one is permeability of gas I over permeability of gas J. Alright. Okay, we are talking back about diffusion coefficient, which is diffusion coefficient is a measure the mobility of the individual molecules in the membrane material. Okay, D. Meanwhile, the absorption coefficient is measure the number of molecules dissolved in the membrane material. Once we call as mobility, which is diffusion. Gas absorption is dissolved. Okay, so if we rearrange back of the selectivity based on the permeability, so we get this equation. Okay, so di over dj means mobility selectivity. Okay, meanwhile ki over kj means sorption selectivity. Okay. Sorry. Where it is. Okay. Okay, we go one by one of the terms. In polymer membrane, the diffusion coefficient decrease with increasing of molecular size. Remember, diffusion D is talking about the mobility of the molecules into the membrane. So sin is the mobility. Just imagine with big person with a smaller person. So which one can move really? Of course, the small person, right? So same goes into the gas molecules. The diffusion coefficient D will be decreased when you have higher molecular size. Okay. With let's say goes back to my example just now. We have big size of people person and smaller size of person. Which one can run faster? Which one can move in longer time? Of course, the smaller person, because the body is not heavy to move. It can move the body freely and in longer time. So same goes to this one. When smaller size of gases should have higher diffusion coefficient. All right. Okay. Because when you have larger molecular size, actually the some of the change interact more on the polymer change. Okay, it's something like you have a pelanggaran between your big molecules and also your polymer membrane. Okay, if you have smaller size of the molecules, then it can move freely towards the membrane material. Okay, so in short, smaller gas molecule which should have higher mobility and give you higher value of diffusion coefficient. However, for mobility selectivity, it depends on whether the membrane material is above or below its glass transition temperature. But what is glass transition temperature? Glass temperature is a range where your temperature change from rigid solid to a softer material. Okay, imagine you have a glass. Okay, glass, when you heat it, you must realize that the glass become melted, but not completely become a liquid, but it's melted. So that is what we call a soft material, when you can reshape the glass. Okay, that is what we call glass transition temperature. If the material is below than the gas transition temperature, the temperature, the polymer is fixed. The polymer membrane, I mean, it fixed and it cannot rotate, and what we call it as a glassy polymer. However, when your temperature of the polymer is above your glass transition temperature, then your polymer is able to move. Okay, because it has enough energy. Alright, then this type of the polymer, we call it as a rubbery polymer. So diffusion coefficient or mobility coefficient is difference between glassy and rubbery polymer. Okay, so we can see here. Okay, let's say we're talking about this rubbery, this rubbery, and this one is one of the example is glassy. Okay, we are going to, because this graph is show you the diffusion coefficient, which is D, mobility selectivity of pentane, which is C5, to nitrogen gases. Okay, for different membrane polymer. Okay, if we are talking about rubbery membrane, right? This is your rubbery membrane. So C5 at where? Something here. Okay, D-pentane to nitrogen. Where is your nitrogen? So your nitrogen is here. Okay, so this one is log 10, so we anti-log 6.5, which is here, 6.5 divided by anti-log of nitrogen, which is here, around here, 5.5. We got it as 10. Remember, this is selectivity, right? Selectivity must be of gas I over gas J. So gas I is your pentane, nitrogen is your gas J. So that's why we divide it, because we want to find the selectivity. Mobility selectivity, or we call it as just diffusivity coefficient here. Okay, this one D. Okay, sorry, diffusivity, mobility selectivity. Okay, all right. So this one is based on rubbery membrane. If you are talking about glassy membrane, where it can be made from PVC, polyvinyl chloride, okay, the equation should be the same because we are going to calculate selectivity, right? So the above one should be the pentane. Where is your pentane here? And over the nitrogen. Where is your nitrogen? Yes, nitrogen. Okay. Okay. Next. Okay. So anti-lock 13.5, which is around here. Sorry, my arrow is okay. 13.5 divided by anti-lock 8.5, you got about 100,000. So you can see that the selectivity of the glass in glassy polymer is much more higher compared to the rubbery membrane. So that is a proof where the diffusion coefficient difference between glassy and rubbery polymer, even though we are talking about the same gases. Alright, hope you understand this. If not, then you can ask me later. Okay, so alright, just now we are talking about mobility, right? The ability of the gas to move. Next, we are going to talk about absorption coefficient, where it measures the energy required for the gas to be absorbed by the polymer. Okay, so basically the absorption coefficient increases with the increasing of permeant condensability. If it's permeant, if we're talking about gas lah. Okay, if the gas has higher boiling point, that means it's easy to condense, and it can be absorbed more, and it should have higher solubility, absorption coefficient. Okay, absorption selectivity actually favors larger and more condensable molecule, such as hydrocarbon vapor, which is got C and H in the change, over the permanent gas. Or what does that mean? Permanent gas is something like oxygen, hydrogen, that is permanent gas. Okay, we look at the example. Okay, you need to find the absorption coefficient of two different sizes of gases in rubbery membrane. So let's say we're talking about pentane and also oxygen. So condensable gas is pentane. Where is your pentane here? So your absorption coefficient is around here, 0.3 something something. But for permanent gas, it is oxygen, is around here, 0.0 something something something. Okay, so that is different size. We have different absorption coefficient. All right. So recall back, permeability is equal to D times S, diffusivity times solubility. Okay, mobility, permeability is between mobility selectivity and absorption selectivity, which is this one is D, this one is S. It's different for glassy and rubbery polymers. Okay, this one is equal to D times S. Can I erase? I want to erase this. Okay. Alright, the permeability for the rubbery polymers and glassy polymer is different, if you can see here, even though we are talking about the same gases. Okay, let's say I want to separate CO2 and nitrogen. Sorry, we doesn't have CO2 here. Okay, let's say we are talking about same. we are talking about butane. So we're talking about I want to separate butane from the nitrogen. So this is your butane. This is your butane, this is your nitrogen. So you can see that the value of the permeability is difference between glassy and also rubbery polymers. Okay. In glassy polymer, which is polyethylamide, is mostly controlled by the mobility. Okay, the diffusion. As the smaller size, which is nitrogen, is smaller than butane, right? Smaller size of the molecule will have higher permeability. But in rubbery polymers, sorption selectivity is dominant, meaning larger molecule will have higher permeability compared to the smaller gases. Okay, so when we are going to separate organic vapor from nitrogen, basically we are preferring to use a rubbery membrane. Okay. Okay, the permeability also the unit of the permeability is 1 bar, which is equal to this unit lah. It's a conversion unit. If you notice in the paper, basically they are using unit of bar. So you should know lah. The bar is mean this of the conversion unit. Okay. So this one is the example of the permeability of rubbery and also glassy material. Okay, if you can see, if you're talking about one of the example, we're talking about silicone rubber, which is it falls under rubbery polymer. We are talking about N2 and CO2, right? Okay. So the permeability of nitrogen is 250. Meanwhile, the permeability of 270 permeability of CO2 is 2700. But in glassy, take cellulose acetate as example. The permeability is only 0.33, but for nitrogen, but permeability of CO2 is 10. Okay. All right. So we go to the next. We are going to learn about the membrane materials and structure. Basically, there are 4 types of the membrane materials. First is metal membrane. So basically, metal membrane can be used for high temperature and high pressure. Basically, they have been used in membrane reactor application, which has the temperature higher than 300. And the first metal membrane is figured when Grahams observed the hydrogen gases formation through the palladium palladium membrane, because the pure palladium able to absorb 600 times of its volume of hydrogen at room temperature. Okay, and hydrogen also can be absorbed by can permeate to other metals such as vanadium, nickel, iron, copper, and etc. Actually, the membrane is highly permeable towards the hydrogen gases, but not for others gases. So this is the mechanism of the gases in the metal membrane. What happens is in hydrogen molecules, uh, the hydrogen is absorbed onto the membrane surface. Then the hydrogen molecules is going to separate into two hydrogen atoms, and due to loss of its electron, as is diffused through the lattice of the membrane, is going to reassociate or combine back and dissolve on the permeate side. So this is what how the hydrogen movement lah in metal membrane. Okay, but it's quite expensive for sure. Secondly, we are going to learn about polymeric membrane. This one is very famous. As you know, polymeric membrane can be glassy and rubbery. Most gas separation actually require selective membrane layer, which is must be very thin, okay, to achieve economical flux. Because when you have bigger layer of the surface layer, it's not surface layer, the thickness is thick, and you giving the resistance to your gases to permeate through. So you have to make sure that your polymer have a very thin layer, and mostly the typical thickness of the membrane actually between 0.1 to 0.5 micrometer. It's very thin. And for gas separation, as we know that if we are talking about diffusion diffusion solution mechanism, the membrane should not have any pores. But when we use a method that been introduced by low absorption reagent, where we use phase separation process, then this type of the membrane produced by this method will have a very small minor defect, or not, or we call it as pore. Very small pore is going to produce. Okay. But in gas separation, we should not have this type of the pores. So what the Monsanto group have been developed or suggest or come up with an idea by sealing, okay, seal the defect by a thin layer of silicone rubber. Okay, this silicone rubber, this silicone rubber actually can able to protect the membrane by using during the handling, and also can close the defect, the minor defect on your membrane. Okay, this thin layer can be coated by silicone rubber or other type of the membrane. Okay, which is, we call it as multi-layer composite structure, where we add another selective layer such as PDMS to one of the mechanisms is to cover your thin, very small pores. Okay, and this also, the selective layer also can be coated another silicone as been proposed by Monsanto group just now. Okay, But however, when we are using the second choice, this one is multi-layer composite structure, is quite difficult to cast because you have a different layer, and in order for you to paste one layer to another layer is quite difficult. Okay, third membrane materials is ceramic and zeolite membrane, where this type of membrane is formed by coating thin selective ceramic or zeolite onto a microporous ceramic support. Okay, basically they are using a soil jet technique, and basically you can find this type of membrane in tubular form. Okay, and then this type of membrane also can be used at high temperature, but for sure this type of membrane is very costly. Okay, and lastly we have mixed matrix membrane, and what the definition of this MMM is combination of zeolite that disperse in a polymer matrix. Okay, as you know, the polymer matrix, meaning polymer membrane, we have some problem in permeability selectivity, and also the membrane in polymer also cannot withstand at high temperature, right? So what we do is they come out with mixed matrix membrane, where the polymer matrix membrane is adding with a zeolite. Okay, because zeolite can withstand high temperature, and zeolite also have high selectivity. So combination of those two is targeted to have high selectivity properties, but with low cost, because we know that membrane from polymer can easy to fabricate. Okay, so it is what MMM stand for, mixed matrix membrane. Okay, that is the last type of the membrane materials that you should know as general. Alright, that's all for gas separation. Next, we are going to learn about pervaporation, which is combination of liquid and gases. Never mind that, we're going to give you a lecture on that. That's all from me. Thank you very much for your attention. Hari Raya is coming around the corner, so dengan 10 jari saya minta maaf ada masalah, ada terkasar bahasa kan, ini kesalahan yang saya buat, so saya minta maaf dan selamat Hari Raya. Maaf saya batin. That's all.